literacy, we are going to take a look at lesson 4.7, the end of the course, mixed equations. So this is a review of most of the equations that we've seen this term. There are a few things that are a little more complicated than this, but the basic types of equations that we've come across are linear. That's where we have a constant rate of change. Stuff that looks like y equals something times x plus some other number. Example of this, suppose I have a car that when it's new is worth $30,000. And that it will depreciate by a constant amount. So instead of a percentage per year like we looked at before, we also looked at a constant amount. So let's suppose it's going to drop by $1,500 per year. And this $1,500 per year, that's a rate, and technically it's called a rate change for this situation. And rate of change is another phrase that means slope. And that is what the M refers to here. So I have a change in dollar amount divided by a change in time. And the B always represents our starting amounts. And sometimes linear equations increase, sometimes like this one, they decrease. So for this one right here, if I wrote it in terms of y, my slope is a negative 1,500 times x plus the starting amount, 30,000. It's always a good idea to state what each variable means. So in this case, y is the value of the car, and x would be time in years. That's an example of a linear equation. We've seen things like that before. And let's try another one. Another popular equation that we've seen would be exponential. The basic type of exponential that we came across is something like y equals a times e to the power x. So an example of something like this, consider problem number 5 in our worksheet, lesson 4.7. Number 5. Up a little. So coral reefs are dying at approximately 10% per year. Write an equation that can be used to determine the future size of a coral reef that has an area of 1,000 kilometers squared. So in this case, a couple of things to consider. We are losing 10% per year. Now, percentage per year lost, we got to start somewhere with percentages, and we always start with 100%. So that means we're going to end up with, after each year, whatever we had originally, 100%, minus the 10% loss. So we're going to retain 90%. So that's our base. We're going to repeatedly multiply by 90% to figure out how much coral reef we have. So in this case, my equation would be y equals the initial amount is the capital A, that's 100 meters squared, times what I retain, which is my 90%, or 0.9 as a decimal, to the power of x. So defining my variables, I In this case, y would be the area of the reef. And x would be time in meters. And that's an example of exponential change, which in this case is percent change. Similar problems we looked at before. We looked at half-life of, say, caffeine, radioactive substances, ibuprofen in the body. So those are also exponential equations. Other types of equations that we worked with were, hang on one sec. Sorry for the interruption. Polynomial type equations or quadratic equations. Quadratic. We haven't looked at those much in the second part of quantitative literacy, but we did in the first part. So examples of quadratic are things involving area. So for example, the area of a circle is pi times the radius squared. The area of a square is just whatever the side length is squared. So here I have the square of a variable, gives me some other result, that's called quadratic. So anytime we have a square involved, it's quadratic. Other related kinds of polynomial, which means we have a variable to a power, is a cubic is another one that came up a few times. Example of a cubic would be, how about a cube, one, which is just the side length cubed, or a sphere, which we'll look at again today, which we saw earlier, which is 4 over 3 times pi times the radius cubed. So there's all kinds of equations out there. Common ones we see in the analysis we do are linear, exponential, and polynomial, in particular power functions like these, and quadratic is one of the most important ones. Another example of a quadratic type equation, consider a rectangle. Rectangle has a length or a base and a height or a width. And the area is just length times width. Now let's make believe this is a photograph of me. Let's just bring my nose there. Oh, not much better. Okay, so if we resize this photograph, we want to do so that's going to keep it proportional. So we don't want to end up, say, changing the length but not the width, because then I will become distorted and not look quite right. Actually, that's a little better in it. Anyway, that's not a real representation of me. So when we resize something, we want to do it proportionally. Suppose we wanted to, somebody said, I need this to be, for example, 25% of the width. Then if it's going to be proportional, I would also have to take 25% of the length, otherwise I'm distorting the image. So what's going to happen there, in terms of the area, is I'm going to have 25% or 0.25 times the length times 0.25 of the width. And if we clean this multiplication up, you can multiply in any order you want. So we could take 0.25 times 0.25, which is, I can't do that in my head. Let's see, I can try. It's 0.625. Double check with the calculator. Oh, crap. I have to share the right screen. Let's back up a touch. I'll try to chop this part out. All right. So, back to the beginning, quantitative literacy, mixed equations. Types of equations that we have seen are linear equations. In a linear equation, you have something of the form y equals mx plus b. where B is the starting amount, and M is a rate of change, also known as a slope, which designates change in one variable, the dependent variable, divided by the change in the other variable, the dependent variable. So here, the amount the car is worth is dependent on the time that goes by. So if I take a new car starting at $30,000 and it depreciates by $15,000 per year, then my equation would end up looking like this one right here, where we have y equals a loss of $15,000 per year times the number of years plus the initial amount. So if 0 years go by, then all that I have is the 30,000. Otherwise, every year that goes by, we lose money. And so it's important to define our variables here. Y is the value of the car, X is the time in years. That's an example of a linear equation. Other equations we've seen in this course are exponential. Exponential equations have some starting amount times some repeated multiple over time, usually. So suppose, like in problem number 5, the coral reef problem, that we have a coral reef is dying at approximately 10% per year. And so as the coral reef dies, it decreases in area. And so if it started at 100 kilometers squared, then here we can demonstrate how much we're losing. Now, in this case, since I have how much I'm losing per year, I have to keep in mind how much I keep, what's left of the coral reef. And so to do that, I have to think with respect to 100%. So we're losing 10% per year. You always start with 100%. Losing the 10% means we retain 90%. So as a decimal, that would be 0.9. So in this case, starting with 100, we're going to lose 90% per year. And so repeated multiples of 0.9 give us an exponential equation here. And so this equation would give us the area of the reef over time. All right, another example. Other types of equations that we've dealt with are quadratic. An example of quadratic equation is anything involving area has two things multiplied. So feet times feet is square feet, or maybe meters squared, miles squared, kilometers squared. Area of a circle is pi times the radius squared. Area of a square is just the side length squared. Sometimes we jump into a higher dimension than the second dimension. 3 dimensions, a cube is the side length cubed. Or a sphere would be 4/3 pi r cubed. So the second power is called a quadratic. Third power is called a cubic. These are examples of power functions or polynomials. So here's an example of an area function in action. Consider the picture of me right here. If we were to change the length but not the width, then that would distort the image. Okay, so instead of having a circular head, I would have a long, tall, oval type head. If we needed to say take 25% of the width, we'd also have to take 25% of the length. So taking 25% of the length times 25% of the width, if we clean that up, 0.25 times 0.25, I think is 0.0625. Let's ask a calculator. 0.25 times 0.25 is, 0.0625. So this is about, actually it's exactly equal to 0.0625 times the length times the width. Now keep in mind, length times width is area. So what happens is when we take 25% of each dimension, the length and the width, what we're going to end up with Now that's, keep in mind with fractions, I have what, oops, 1/4 times 1/4, which makes this 1/16. We'll see that in just a moment. So I end up with a new area that's equal to 1/16 of the old area. And so this ends up giving me a quadratic equation. Oh, here it is, got an extra R today. Let's get rid of that. The 1/16 came from 1/4 times 1/4. So essentially what I have there is 1/4 squared times, times the old area. And the 1/4 came from the amount I tried to decrease my width by. And if I want to keep the length proportional, I have to do the same thing there. So what we have is a new equation here. So the new area can be found if we have a proportional image, and that extra R again, by whatever the fraction reduction is. Let's call that F. We're taking some fraction of the length. If we square that, because we have to take the same fraction of the width, and we multiply by that by the old area. So this is a quadratic equation relating resizing an image. And it works if you try to make the image bigger also. And so if we look back at this image right here, and I tried to take 1/4 of this image, so this length right here is about 1/4, I would also have to take 1/4 of the width here, and that would be about this chunk here. So my new image should be this big right there. And if you think about it, I've broken this into a 4x4 grid. Each little rectangle is the same proportions of the big rectangle, and there's 16 of them, little ones and the big ones. So this little one is definitely 1/16 of the big one. Right? So we have to square our reducing or multiplying factor in order to compare length to area. And that's a classic example of working with a power function, or in this case, quadratic. All right, let's take a look at another one. So we're going to get a wee bit more complicated. Consider the equation of the volume of a sphere, and that's 4 pi over 3 times the radius cubed. We're going to jump into one of the last problems in this section. Scroll down to it, which relates to volume and densities. This is some pretty cool stuff. Almost there. I'll play around with these other problems another day. Okay, so like considering a hot air balloon. So the air or gas we put into a balloon is going to be, if it's lighter than the air around it, it will float. Right? Similar thing happens with buoyancy in water. And so to figure that out, we need to consider density of an object. Density is mass, how much material is crammed into a given volume. So for example, consider a ball of wood versus a ball of metal, and both are solid. There's more material packed dense tight into the metal, and then the wood has more space on the inside of it. And so the metal has a higher density than the wood. So we have this relationship here that density is equal to mass over volume. So we're going to play around with that a little bit on paper and on a spreadsheet. So some things that are going to be important to us here, this equation, density equals mass over volume. That water has a density of about 1 gram per cubic centimeter. That, let's see, where's the other one? That steel has a density of about 8 grams per cubic centimeter. And we're going to take a look at some balls, a solid one and a hollow one, both made out of 100 grams of material. And grams are a measure of mass, not a measure of weight. So for example, one of these balls with 100 grams of metal has the same 100 grams whether it's on Earth or on the moon. However, it will weigh different in each spot. Okay? Kilograms are also a measure of mass, not weight. So for example, let's say I weigh 80 kilograms on Earth, I will also weigh 80 kilograms on the moon. I'm misspeaking here actually because I said weigh. It's actual mass, not weight. Weight considers gravity, and gravity of the moon is different than gravity of the Earth. It's a whole other discussion. Let's get back to density and mass. We're going to answer some of these questions here, and then we're going to take a look at this table and this next relationship between the volume of a sphere and the radius with mass and density involved. Okay, so let's do it. So things that we need to consider here are the volume of a sphere. We also need to consider that density is equal to mass divided by volume. So how much stuff divided by the space you put it in gives you how dense it is. We can write this mass density volume equation in different ways. For example, we could multiply the volume to the left, divide the density to the right, and so we get an equivalent equation that says volume is equal to mass over density. And an alternative version of that would be to isolate mass, multiplying density to the other side, or volume, vice versa. And then we get that mass is equal to density times volume. So those are the three versions of that equation that can come in handy here. The first question we are asked to consider: what happens to the density question mark as the volume increases? So we let the volume go up. So that would be like blowing up a balloon, right? And here, something to consider is that to do this, the mass is going to be held constant. Mass is constant. So for example, with the ball example, so we start with a solid ball of 100 grams, and then we melt it down and we make it we cast it into a hollow sphere. That sphere will be bigger because there's empty space inside. Okay, so we made the volume bigger. But what's going to happen with the density? So remember that density is equal to mass over volume. And let's consider a simple example where the mass is 1. If the volume was 1, the density is 1. If we take that same mass of 1 and we make it twice the volume, notice then the density becomes 1/2, right? Mass over volume. Or, oops, not equals, just another example. Or if we kept the mass fixed at 1 and we made the volume 3 times bigger, notice as the volume increases, so I'm increasing the volume here, the density in this case is the whole fraction, and the fraction is decreasing. So that tells me that density decreases as volume increases. So density, the fraction, decreases. Right? And that makes sense. If you put a bigger denominator in the fraction, the whole thing is smaller. Right? Think of a slice. Think of a pizza. Cut the pizza in half, you get a big slice. You cut it into 8ths, and you get a little bitty slice. Okay, so more slices, less. Each piece is smaller, and that's what this represents here. So that's number 35. We want to use the density formula to determine the volume of the steel ball. So let's see. What do we know for this next part? So question number 36. we know that density is equal to mass over volume. And so we're given earlier that the density of steel is 8 grams per cubic centimeter. So that's my density. And the mass that we're given with is 100 grams of steel to work with. And we need to figure out the volume. So here we could consider a little cross multiplying and dividing. So we're going to get V times 8 grams is equal to 100 grams times centimeters cubed. And then we want to get the volume alone, so we'll divide the 8 grams over. So volume in this case is 100 grams divided by 8 grams times centimeter cubed. And I kept the units in here just to demonstrate that the grams will divide out, leaving centimeters cubed, which is a unit of volume. And so let's see, how many times does 8 go into 100? Let's see, we cut it in half once, we get 50, then 25, then 12.5. So what I get is 12.5 centimeters cubed is the volume of my solid steel ball. Next, to figure out what the radius of that ball is, so this would be the smaller version of the ball, we'll have to take our equation for the volume of a sphere, which is 4 pi over 3 times the radius cubed, set that equal to our volume, and solve for the radius. So to solve here, I can multiply by the reciprocal of this fraction. So that's going to give me that r cubed is equal to 3 over 4 pi times that 12.5, which we could rewrite if you think about this as multiplying two fractions. That's 3 times 12.5 divided by 4 times pi. And we get the r alone, we learned about a cube root or the 1/3 power. So r on its own is going to be equal to that fraction, 3 times 12.5. I'm going to wait to plug this into my calculator. All raised to the power 1/3, because the power 1/3 undoes the power of 3. So I'm going to enter that into my Google calculator and see what I get. I have to be careful with parentheses. Google. Let's just type 2 plus 2 to bring up the calculator. All right, so we have here parentheses 3 times 12.5. That one's okay. The denominator is complicated, so when I divide, I have to put the denominator in parentheses and write it as 4 times pi. All right, close the denominator, close the fraction, and then raise it to the power, parentheses. My tablet just died. Parentheses, where is it? 1 over 3. Ah, tablet's dead. Bummer. Okay, so I get about 1.439. And my writing tool, my tablet, just bit the bullet. The charger apparently isn't working. So we just calculated the radius of a steel ball that has a volume of 12.5 centimeters. All right, so I'm going to have to switch over to a spreadsheet to finish this up. So that was number 37, the 1.4397. And that's measured in centimeters because we took the cube root of centimeters cubed. Okay, what we're going to do next is in a spreadsheet, we're going to build this table and these graphs And then I'm going to have to come back to the rest of this on another recording because I have nothing to write on at the moment. So spreadsheet. So I started building this right here. Some things to note. What do we have? We have an initial volume. Volume, oh, I can't see it all. Volume, let's call it 0, is 12.5 centimeters cubed. And that gave us an initial radius of about, actually I can calculate it here just to double check. Equals, let's see, where were we? We were 3 times 12.5 divided by parentheses 4 times pi, which needs a little parentheses on it itself. The whole thing is raised to the power of 1/3, parentheses, and that should give me y 1.44-ish for the radius. So over here, I made some calculations, and let's see if I did them right. So here I'm assuming the radius is 1.5, which is just a little bigger than what I have, 2, 2.5, and 3. The volume of a sphere is 4 pi, this is how you enter pi on a spreadsheet, divided by 3 times the radius, which is located in column A, cubed. So here I just typed in that formula, hit enter, and then filled it down. So that gives me the volumes of balls that have radius 1.5 centimeters, 2 centimeters, 2.53, and 3.5. To calculate density, we take our mass and divide by volume. And so the mass, we're fixed. We only have 100 grams of steel to work with. So as the volume gets bigger, we have a bigger hollow core. We should see the density drops, and we can see that here. So I just took, for density, I set it equal to my mass, 100, divided by my volume, which is changing with the size of the ball. And then I fill that down. So I can see here, as volume increases, density drops, which is what we predicted earlier when we were messing around. Looking at the graphs of these, so if I ask the computer to graph radius versus volume, I get this graph here, and I can see as the radius increases, the volume increases. And if you put a line to that, you'll see they don't quite line up or straight edge to that. Okay. This is curving upward. Alternatively, if we take a look at the radius, and to highlight two separate things, you hold after your first selection, let go of the mouse, hold Control, highlight your second selection. And then I can create a new chart. And that screen is too big. Shrink it down. And I scroll through until I see my scatter plot. So I can see radius versus density. So as the radius increases, the density drops. So I have radius going this way and density going that way. We labeled that here, radius versus density. So we can see small radius, high density. If we have a big radius, we have a low density because we're keeping the same amount of material. Kind of like blowing up a balloon, but ours is made of steel. And then the last graph I made was volume versus density. And that's right here. And so as the volume increases, we can see the density dropping. And notice it does not do so in a straight line. It's not exponential either. It's a different kind of function, a cube root function. All right. So I'm going to stop this here. If I haven't edited the video by now, then there's a little part about a quarter of the way in where I'm talking and you can't see my screen, which I remedy shortly after. I'll catch you all soon. Have a good day. Hello. It's shadowy. Goodbye.